Good morning, all. I am Dr. Pravat Ranjan Pati, Department of Mechanical Engineering, going to deliver the one of the subject that is called thermal engineering. This is a core course. This is undergraduate fifth semester course, mechanical engineering. This is thermal engineering. If you see, this is an undergraduate course. If you see the objective of this course, what student will learn from this course. So the usage of fundamental knowledge on the thermodynamic cycles. Now we will recall the thermodynamics, all the thermodynamic cycles that were studied in thermodynamics and applied thermodynamics, like your air standard cycles, vapor power cycles. But we are going to specifically studies on vapor power cycles in this course, and fluid dynamics phenomena present in the turbo machines and combustion for producing electric and mechanical engineering powers. Now, the operational costs, principles, features, procedures, and detailed thermodynamic analysis related to components of power cycles, rocket propulsions, jet propulsions, we're going to study in this semesters, in this course. A wealthy of real-world engineering problems and examples towards gaining the experience for designing and developing power generating systems in the engineering practice. So these are the core objectives of this particular course, that is called thermal engineering. Now we'll go to the basic concepts. What are the basic concepts of thermal engineering? And this is the first chapter we're going to study in thermal engineering. The first one is thermodynamic vapor power cycles. Already we have studied all the thermodynamic cycles in thermodynamics and applied thermodynamics, like air standard cycles and vapor power cycles. Air standard cycles means we have studied already in Otto cycles, diesels, and dual cycles. In vapor power cycles, already we have discussed Carnot cycles, Rankine cycles. Already we have studied. Now we have to recall all these cycles, mostly vapor power cycles in thermal engineering. So in a vapor power cycle, if you see, all the theory remains same. What are the principles and working principles all remain same to air standard cycles, but the only difference is in air standard cycles we are using refrigerant is air, but in vapor power cycles we are using the refrigerant is vapor. So or steam. This is steam. So that is the basic difference between the air standard cycle and vapor power cycles. Now, this steam is maybe in the form of wet steam or dry steam or superheated steam. And these are the conditions of steams which we are going to study. Now, there are many vapor power cycles, but we are going to study only focused on Carnot cycle and Rankine cycle. Now, we'll study about Carnot cycle with steam as a working substance. Previously, we have done the Carnot cycle where we are using the working substance is air. Now, we are using the steam as a working substance. Now, these are the main components of Carnot cycle. First one is boiler, second is turbine, third one is condenser, and fourth one is compressor. Now, how it works, what is the principle, how it is works, the Carnot cycle. Now we're going to study. Let us consider a 1 kg of steam. Here, let us consider a 1 kg of steam is going into the turbines. So, what about the turbine? And this 1 kg of steam is going entering the turbine where it expands isentropically. Where it expands isentropic to the and after expansion it will becomes wet steam. Now basically previously it is dry steam, 1 kg of dry steam. Now when it enters the turbine and after expansion it will becomes wet steam. Now this wet steam is going to the condenser where we are supplying the cooling water here. Why we are supplying cooling water? If you are supplying cooling water, the heat is rejected. Here heat is rejected. So here the wet steam is going to be condensed. Now, after condensation it will becomes the wet after condensation it will becomes the steam. When it is going again, it is going to the compressor where it is compressed isentropically. Here the wet steam is compressed isentropically. After compression it will becomes the again saturated liquid. Now it is going to the boiler. Now where again this we are supplying the heat in the boiler at a constant pressure process. Now again after supplying the heat into the boiler at a constant pressure process, the saturated liquid becomes the dry steam. Again the cycle is going on. Again this same cycling process is going on. Now the cycle is completed. Now this is the working principle of Carnot cycle where we are using steam as a working substance. Now these are the four. If you see in the TS diagram or PV diagram, if you draw the temperature entropy diagram on pressure volume diagram of Carnot cycle. So this is the diagram. See, this is the saturated liquid line, and this is the saturated vapor line. Sorry, this saturated vapor line. And initially, if you see, the steam is in saturated liquid point. This is a saturated liquid in the boiler. Now, 1 kg of steam is going to the turbine. Here it is dry saturated, right? After expansion, it is going to the condenser, where it is condensed, where the heat is rejected, right? Now here it is wet steam. Now again, this steam is going to the compressor, where it is compressed isentropically, right? It is compressed isentropically, and it becomes saturated liquid. Now this is the TH diagram of Carnot cycle, and this is the PV diagram of Carnot cycle. Now you see, we'll see what are the 4 processes. This 1 to 2 already we know. Already I have told. This is a boiler. Here the saturated water at point 1. Already I have discussed all these points. At point 1 is isothermally converted into dry saturated steam in a boiler. Thus, the heat is absorbed at constant temperature, where at T1 and pressure P1 during these operations. Here, heat is absorbed, right? Suppose let's say this is Q1, and here again this 2 to 3 process is called reversible adiabatic process or isentropic expansion process. And what is during this process, the steam is expanded isentropically to a temperature T2 and pressure P2, and the point 3 represents the condition of steam, where it is the wet steam, right? After expansion, this 3 to 4 is called condenser. So during these operations, if you see, heat is rejected at constant pressure P2 and temperature T3. As the steam exhausts, it becomes wetter and cooled from 3 to 4. It is where it is cooled. Here we are supplying water, cooling water, so that it is cooled. That means here heat is rejected. Let's say this is Q2, right? Now this 4 to 1, if you see this 4 to 1, the wet steam at 4 point is compressed isentropically. This is the isentropic process. It is compressed isentropically. This is a reversible adiabatic compression process till the steam regains its original state. Originally, it is in saturated liquid, right? Now, after compression, it will become saturated liquid at temperature T1 and pressure P1, and then the cycle is completed. Now, if you see here, heat is absorbed, that is Q1. Sorry, heat is absorbed Q1, and this is heat rejected Q2, right? Now, this is the compressor work, and this is the turbine work, right? WT. Now, how to calculate the efficiency of Carnot cycle? Now, how to calculate the heat absorbed? Suppose here it is heat absorbed. Let's say Q12. This is Q12, right? So, what is heat absorbed? How to calculate heat absorbed? We know the entropy change. We know the entropy change. The entropy change is equal to heat transfer divided by temperature, right? This already we are knowing the entropy in thermodynamics. The change in entropy, that is equal to heat transfer by temperature. So, what is heat transfer? Equal to T into ds, temperature into entropy. Now, that we are using here. What is the heat absorbed here? Q12 is equal to, this is change in entropy, right? We are considering the process 1 to 2. So, this is S2 minus S1 is change in entropy into temperature T1. This is a temperature T1. Or we can say here, see, this is isothermal process. This is T1 is equal to T2, and this one is T3 is equal to T4. And this is S1 isentropic expansion process, compression process. S1 is equal to S4, and this is S2 is equal to S3. So now this is the heat absorbed, S2 minus S1 into T1, or you can write S2 minus S1 into T2. How to calculate heat rejection? So this is heat rejection in condenser Q34. This is 3 to 4 process. We are calculating the heat rejection process. So heat rejection is same, S2 minus S1. We can write C, S3 is equal to S4. We can write it here, that equal to S3 minus S4 into T3, or that equal to S3 minus S4 into T4, since T3 is equal to T4. Or we can write this is isentropic process, right? So S2 is equal to S3, so we can write it here S2 instead of S3, and S4 is equal to S1, so we can write it here S1. So this is how to calculate the heat absorbed, S2 minus S1 into T3 or S2 minus S1 into T4. Now if you see the process 2 to 3 and 4 to 1, these two processes where there is no heat of exchange of heat during this process, because this is isentropic process. Now there is no heat rejection, no heat transfer takes place. So what is the net work done? How to calculate the net work done? The heat absorbed minus heat rejected. So what is the heat absorbed we have calculated? S2 minus S1 into T1 minus S2 minus S1 into T3. If you take this S2 minus S1 outside, so this S2 minus S1 into T1 minus T3. So this is the net work done during the cycle. Next, how to calculate the efficiency? And efficiency, already we know the efficiency of cycle is equal to, this is output by input. So what is the output here? That output nothing but the work done by the cycle, and input is the heat absorbed, that equal to 1 to 2, right? So already we have calculated work done, right? Work done is equal to S2 minus S1 into T1 minus T3 divided by what is the heat supply? S2 minus S1 T1 minus S2 minus S1 into T1. So if you see, this will be cancelled. So this is equal to T1 minus T3 divided by T1, or we can write it as 1 minus T3 by T1. So this is how to calculate the efficiency of Carnot cycle, where this T1 is the highest temperature according to the boiler pressure, where the pressure is remains constant, P1 is equal to P2, and T3 is the lowest temperature corresponding to the condenser pressure, where the P3 is equal to P4. This is how to calculate the efficiency of Carnot cycle. So this is all about the Carnot cycle. So let us now will solve one numerical based on this Carnot cycle. Now the question is, a power plant. So this is a power plant, steam power plant, where we are using Carnot cycle, is supplied with a dry saturated steam. Now the condition of steam is given dry saturated, right, at a pressure of 16 bar. Now the initial pressure is given 16 bar and exhaust at the pressure of 0.2 bar, and P2 exit pressure is given 0.2 bar, right? Now we are using the steam table here. So using this steam table, calculate the efficiency of Carnot cycle, right? So already we have discussed the efficiency of Carnot cycle is equal to T1 minus T3 by T1, right? So what is T1? We have to calculate the T1. Now, if you see the first condition, if you see the steam table on this T1 and T3, we are finding the value of T1 and T3 from steam tables. Now the first condition is given pressure 16 bar, right? So at pressure 16 bar, what is the temperature T1 from steam table? If you see in the steam table, sorry, if you see in steam table, there are three tables. First one is saturation pressure table. Second is saturation temperature table, and third one is superheater table. This is the steam table. If you see the steam table, first page is saturation pressure, and the pressure is given in bar, like 0.1, 0.2, 0.1, 0.2, 0.3, like that it is given. And temperature is given in degree Celsius, like 100, 150, 160, 130, like that it is given. And superheated also value is given. Now we have to find out the value of temperature T1 at the pressure P1. So here the condition is given at first condition is given, initial pressure is P1 16 bar. Now we see the steam table at saturation pressure table. What is the pressure 16 bar? Now where is the pressure 16 bar? If you see the, suppose let's say the 16 bar is here. Now what is the corresponding temperature here? Okay. Now from steam table at pressure 16 bar, what is the corresponding temperature? So that temperature is called T1. So that is 201.4 degrees Celsius. Now we convert to Kelvin, plus 273 watt it will becomes in Kelvin. Next, initial condition at pressure, final condition pressure P2 is given 0.2 bar. Again same pressure 0.2 bar. What is the corresponding temperature? What is the corresponding temperature? And that temperature is called T3. So this is becomes 60.1 degrees Celsius. Now if you add this 273, it will becomes 333.1 Kelvin. Now you can easily calculate the efficiency of Carnot cycle, right? So efficiency is equal to T1 minus T3 by T1. So this minus this T1, 474 minus 33 by 474. This is equal to 0.298. Nothing but this is 29.8%. So this is how to calculate the efficiency of Carnot cycle. In a Carnot cycle, heat is supplied at 350 degrees Celsius. So initial condition is given temperature 350 degrees Celsius. Now in previous questions, the initial condition pressure is given 16 bar. Now here the temperature is given 350 degrees Celsius, right? And is rejected at 25 degrees Celsius. So this is temperature T1 is given 350 degrees Celsius and temperature T2 is given 25 degrees Celsius. The working fluid is water here. We are taking the working fluid is water, which while receiving heat and evaporates from liquid at 350 degrees Celsius to steam at 350 degrees Celsius, right? From the steam table, the entropy change for this process is given 1.438. The entropy change is given. That means change in entropy. That means the ds is equal to is given 1.438 kilojoule per kg Kelvin. The change in entropy is given 1.348. Now we have to calculate for 1 kg of water what is the heat supplied, what is the work done, and what is the heat rejected per cycle. Now how to calculate? Now if you see the heat supply in the boiler, to calculate H2 minus S1 into temperature T1, right? So already this change in entropy that equal to H2 minus S1 is given 1.438. This into T1 is given 350 degrees Celsius. By convert to Kelvin, then you can calculate what is the heat supply per cycle. This is called 895 kJ per kg, right? Next, what is the work done per cycle? The work done already we have calculated in the previous section. That is H2 minus S1 into T1 minus T3, right? Or you can calculate first heat rejection, then you can go for the work done. How to calculate heat rejection? H2 minus S1 into T3. That means this H2 minus S1 is this 1.438 and T3 is equal to 25 degrees Celsius. So this T3. Then convert to Kelvin. So 298 Kelvin. So after calculation of heat rejection, work done is equal to work done is equal to heat absorbed minus heat rejected, right? So heat absorbed is H2 minus S1 T1 minus H2 minus S1 into T1 minus H2 minus S1 into T3. Now if you take H2 minus S1 outside, this is T1 minus T3 that we have written here. So H2 minus S1 is 1.438, right? And T1 already is data is given 623 Kelvin minus 298. So the return becomes 467.35 kJ per kg. So this is all about Carnot cycle. Now the next most working cycle that we are using in steam power plant is Rankine cycle. So this is the most important cycle, Rankine vapor power cycle, that already we have studied in your applied thermodynamics. Now let us again recall it. So Rankine cycle is a theoretical cycle. It is a theoretical cycle on which the steam turbine works, right? Here we are using the steam as a working substance, and this Rankine cycle is usually used in steam power plant. Now it is an ideal cycle. This is ideal cycle. We are considering ideal cycle for comparing the performance of steam turbines, steam plants, and it is a modified form of Carnot cycle. Simply modified form of Carnot cycle in which the condensation process, that is 3 to 4. So this is a condensation process, right? 3 to 4 is continued until the steam is condensed into the water. Now, if you see, these are the four basic. These are the components of Rankine cycle. If you see in Carnot cycle, we have boiler, turbine, condenser, and compressor. Right? But in Rankine cycle, if you see boiler, turbine, condenser, instead of compressor, we are using feed pump. Right? We are using feed pumps. So the major components of Rankine cycle is boiler, turbine, condenser, and feed pump. Now, let us consider a 1 kg of steam here. 1 kg of steam is going into the turbine, entering the turbine. Now, after expansion, asyntropically, it becomes wet steam, right? Same process. What we have done in the Carnot cycle, this wet steam is going to the condenser, where the heat rejection takes place by supplying the cooling water. Right? Where heat is rejected. Now, this wet steam is going to the compressor, in case of Carnot cycle, where it is compressed till it becomes saturated liquid. But here, the wet steam is condensed continuously until the steam is condensed into the water. So that is the difference between Rankine cycle and Carnot cycle. Now here, the wet steam is condensed continuously in the condenser until it becomes saturated liquid. Now this saturated liquid is going to the boiler. Now how it is going to the boiler? It is raised by the feed pump. And this feed pump, using this feed pump, this saturated liquid is fed to the boilers, where we are supplying the work to the pump. Now again, the saturated liquid is going to the into the boiler, where we are supplying heat in the boiler. Here there is saturated liquid supplying heat to the boiler. Now after this saturated liquid is heated, it will becomes the steam. And this again, this 1 kg of steam is going to the turbine. Now this cycle is completed. And this is the working principle of Rankine cycle. Now, if you see the TS and PV diagram, what we have discussed in the previous cycle, in Carnot cycle, is same here. The temperature entropy diagram and pressure volume diagram for Carnot cycle. Sorry, for Rankine cycle. Now, already we have discussed the working principle of Rankine cycle. Now, if you see, already I have told, when the 1 kg of steam is going into the boiler, before it, going to the entering into the turbine, before entering into the turbine, the condition of steam, it may be dry saturated, it may be wet steam, it may be superheated steam. So if you see the diagram here, let's say this is the TS diagram, right? Now if you consider this steam, here it is a dry saturated steam, and this dry saturated steam is entering into the turbine, right? Where it is expanded isentropically in a turbine. So after expansion, it will becomes wet steam. Now this wet steam is going to the condenser, where let's say this is point 2. At this point 2, this condenser wet steam is going to the condenser, right? The heat is rejected, and it will becomes, and this condensation process takes place continuously, where this wet steam is converted into saturated liquid, and this is going to the boiler. So how it is going to the boiler? Here there is a pump where we are giving the work input to the pump. Let's say WP. We are using the pump. Using this pump, again it is going to the boiler. This liquid. Now the process is completed. If you see, the process is completed. Now here, if you see, before entering into the turbine, the condition of steam is dry saturated. Now if it is, it may be dry saturated, or it may be superheated, or it may be wet steam. That's why this diagram is looking like this. If you see this first diagram, here it is dry saturated, the condition. Now if it is a superheated steam, then the point should be here. This 1, 2, 3, 4. 1 double dash, 2 double dash, right? If it is a wet steam, and the point should be here. So what is process 1 to 2? This process 1 to 2 is called reversible adiabatic expansion process in a turbine, or it is called isentropic expansion process. Now this 2 to 3 is a constant pressure transfer of heat in the condenser, right? That means this 2 to 3 were rejecting heat. Let's say this is Q2. Heat is rejected in the condenser. 3 to 4, this is a reversible adiabatic pumping process, right? In the heat pump or isentropic process. And 4 to 1, here we are supplying the heat. 4 to 1, here we are supplying heat to the boiler. So this is suppose Q1. So now if you see, this is a boiler. 4 to 1 is boiler, 1 to 2 is turbine, 2 to 3 is condenser, 3 to 4 is pump. Now this is Q1 is heat absorbed in the boiler, and Q2 is heat rejected in the boiler. Now we have to calculate the efficiency of Rankine cycle. As we have earlier calculated the efficiency of Carnot cycle, like that we have to calculate the efficiency of Rankine cycle. So how to calculate? Already I have told, let us consider a 1 kg of liquid, right? Now we are applying the steady flow energy balance equation, SFEE. That is called steady flow energy balance equation. Already we have studied in the thermodynamics, first law of thermodynamics. That is applied to flow process, steady flow energy balance equation. Now we are applying the steady flow energy balance equation to the boiler, turbine, condenser pump. Now let us draw a TS diagram. So this is a TS diagram of Carnot cycle. Let us assume the condition of steam is bisaturated here. This is 1 point, 2, 3. This is pump, isentropic, 4 and 1. Right. Here heat is rejected. This is Q. Sorry, heat is absorbed Q1. Here heat is rejected Q2. This is turbine work, and this one is pump work. Right. Now, so 4 to 1 is a boiler, 1 to 2 is turbine, 2 to 3 is a condenser. Now we are applying the steady flow energy balance equation to this boiler, turbine, and condenser. Right. Now consider first boiler, first one. Now we are applying the steady flow energy balance equation to the boiler. What is the steady flow energy balance equation? 4 to 1. If you write the 4 to 1 process for boiler, H4 plus kinetic energy V4 square by 2 plus Z4G potential energy plus heat transfer is equal to H1, this point, plus V1 square by 2 plus Z1G plus work transfer. Now in the boiler, if you see, there is no work transfer, so this is 0. We are neglecting the potential energies, right? Now, so what is the H4 after putting the neglecting the potential energy and heat and work transfer? So H4 and kinetic energy we are neglecting. By neglecting the kinetic energy, potential energy, and heat work transfer, the equation becomes H4 is equal to H4 plus Q, where heat is supplying, that is Q1, is equal to H1. So this is the steady flow energy equation for a boiler, where here it is written. Why it is called H4, HF4? HFC in steam table there is a HF and HFG. The F and G term is coming. F for fluid or liquid, G for gas. So HF, what is H? Specific enthalpy, right? So at 4 point, this is in liquid region, right? This is liquid region and this is vapor region. At 4 point, this is in liquid region. That's why it is written H4 and HF4. So HF4 plus Q1, already we derived this, is equal to H1. Now calculate Q1. Our aim is to calculate what is the heat absorbed, that equal to H1 minus H4. Right? So this is the heat absorbed during the constant pressure process. Now again, we are applying the steady flow energy equation to the turbine. So what is turbine? 1 to 2. If you apply for turbine, same equations, you have to write H1 plus kinetic energy V1 square by 2. We are neglecting the kinetic energy, plus potential energy we are neglecting, plus heat transfer also we are neglecting. Now H1 is equal to H2 plus same heat transfer potential energy, kinetic energy are negligible, then it becomes work transfer, that is called turbine work. So what is the turbine work here? That is equal to H1 minus H2. So this is the turbine work during the 1 to 2 process. Again, we are going to apply the steady flow energy equation for a condenser. Now, which one is the condenser? 2 to 3. Now, we are going to apply the steady flow energy equation for a condenser because we have to calculate what is the heat rejection. So, if you apply the steady flow energy equations, what is that? H2 by neglecting potential energy, kinetic energy plus heat transfer is equal to H3. So, what is Q2? Sorry, what is Q2? That equal to H2 minus H3. So, what is 3? That equal to H2 minus HF3, because this 3 point is in liquid region. So this becomes H2 minus H3. So this is the heat rejection. So after calculating heat absorbed, heat rejection and turbine work, now let us go into the heat pump. Heat pump. That pump is called 3 to 4 process, pumping process. Okay. Again, we are applying the steady flow energy equation to the pump. So if you write the steady flow energy equation to the pump, so this is the equation, right? So H3 by neglecting the kinetic energy, potential energy, heat transfer plus pump work is equal to H4. So what is the pump work? That equal to H3 minus H4. So this is the pump work, right? And this, if you see here, the 3 and 4 point are in liquid region. That's why we are taking HF3 and HF4. So this pump work will becomes, sorry, H4 minus H3. Yes, this will becomes H4 minus H3. H4 minus H3. Now this pump work will be on H4 minus H3. So now how to calculate the efficiency of a Rankine cycle? So the efficiency of Rankine cycle is equal to, already we know the efficiency is equal to general efficiency output by input. Here efficiency will be the work done by heat input is the heat supply. Input is the heat supply, right? Now in previous Carnot cycle, we're using only the work done, right? Heat absorb minus heat rejection. The difference between the heat absorb and heat rejection, that is called work done. But here there are turbine work and pump work. Now we are considering the net work done. What is the net work done divided by heat supply? That is called efficiency of Rankine cycle. So what is the net work done here? The net work done is equal to turbine work minus pump work. Already we calculated turbine work and we calculated pump work, and the efficiency will be turbine work minus pump work. What is turbine work? H1 minus H2. What is pump work? H4 minus H3. And Q1 is equal to H1 minus H4. Now if you see, the feed pump handles the liquid water which is incompressible. The feed where the liquid is incompressible. That means if you increase the pressure of the water, saturated water, its density and specific volume slightly change, right? So using the thermodynamic relations for reversible adiabatic compression process, this 3 to 4 is called reversible adiabatic compression process. Now we are going to apply the thermodynamic relations. What are the thermodynamic relations we are going to apply? TDS is equal to dH minus VdP. Now, how it becomes TDS equal to dH minus VdP? We know the enthalpy H, specific enthalpy U plus PV, right? Now, if you differentiate, and dH is equal to du plus PdV plus VdP. Now, what is du plus PdV? This is called work done, right? Yes, this is called work done. Because not work done. Your first law of thermodynamics says heat transfer minus work transfer is equal to du, right? So what is heat transfer? It's equal to du plus work done. What is work done? Equal to PdV. Already we had discussed in the thermodynamics. So this heat transfer is equal to du plus PdV. So instead of du plus PdV, you put this del Q. So dH is equal to dQ plus VdP. Now, this, what is dQ? That equal to TdS plus VdP. Now, what is TdS? That equal to dH minus VdP. That already we here. Since the 3 to 4 process is isentropy process, the change in entropy becomes 0. Now, it will be, if it is 0, now this dH is equal to VdP. This one, or delta H is equal to V delta P, right? Now, what is this delta H? We're considering the pump, right? That equal to H4 minus H3. That equal to, what is this V? Specific volume. So let's say this is V3, initial volume. What is this pressure? P4 minus P3. So this is the pump work. Now already we know the feed pump term. This is the pump work, WP, right? H4 minus H3. And this pump work is very small quantity if you compare it with the turbine work. Now this, after neglecting the pump work, the efficiency of Rankine cycle becomes H1 minus H2 by H1 minus H4. So this is the efficiency of Rankine cycle. So next class, we will discuss about some problems, numericals associated with the Rankine cycles, and how it can be used, how it can be utilized in a steam power plant. That we will discuss in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.